How far can we actually travel in space in one human lifetime if we throw everything we have at the problem? In this video, we're going to take your 80 years, line them up against the speed of light, the fastest probes we've ever launched, nuclear and fusion engines, even near light speed starships, and see exactly where the universe forces you to stop. Can a real person ever reach another star? Or are we permanently stuck orbiting our own sun, no matter how good our rockets get? Stay with this, because by the end, you'll know the hard limit on how far a human body with real physics and real tech can actually move through the universe before the clock runs out. But before we continue, please subscribe to the channel to give your support. Let's continue. Here is a hard number to start with. Your life is roughly 80 years long, and physics does not care about your dreams. It only cares about that time and your speed. If you turn those 80 years into pure seconds, you get around 2.5 billion seconds. That is your full budget. Every moment from birth to death, and every mile you ever travel through space has to fit inside that budget. Now compare that clock to the fastest thing that can move. Light crosses space at about 186,000 miles per hour, around 300,000 kilometers per second. If a beam of light had those same 2.5 billion seconds, it would cover about 80 light years in one human lifetime, which comes out to roughly 470 trillion miles, about 760 trillion kilometers. So the absolute upper limit for distance in one lifetime, written in the language of the universe, is around 80 light years. Now here is the problem. You are not light. You have mass. You need a ship. The ship needs fuel, and the laws of relativity say that anything with mass can never reach the speed of light. So your real question is not how far could light go while you are alive. The real question is how close can you get using real engines, real fuel, and the fragile human body before the clock hits zero? And the honest answer, based on what we have today, is not very close at all. So let's drop the fantasy of moving at light speed and look at the fastest human-made objects humans have actually built. How bad is the gap between our record speeds and the cosmic speed limit? The fastest human-made object so far is the Parker Solar Probe. It is a small robotic spacecraft we sent on a path that dives very close to the sun, using the sun's gravity to sling it to extreme speeds. Near its closest passes, Parker has reached about 430,000 miles per hour, roughly 690,000 kilometers per hour. That works out to around 125 miles per second, about 200 kilometers per second. In everyday terms, that sounds ridiculous. It is fast enough to go around Earth in a few minutes. But when you put that next to the speed of light, the picture gets harsh very quickly. Parker is only moving at about 0.064% of light speed. Not 1%, not even a tenth of a percent, just a tiny slice of a single percent. At that speed, crossing one light year would still take well over 1,000 years. So here's the first hard reality. Even our fastest probe is crawling on the scale of stars. If you had a ship that could cruise at Parker's top speed for your entire life, from birth to age 80, you would still not even reach the nearest star. Your lifetime would run out while you are still deep in the dark between the sun and its neighbors. You might push back and say, fine, that probe has not been flying very long. Maybe the trick is not just higher speed, maybe the trick is staying in flight for decades. So what happens if you let something run for half a human lifetime? That's where Voyager 1 comes in. Voyager 1 launched in 1977, and it's been traveling for nearly 50 years straight. It swung past Jupiter and Saturn, picked up some extra speed from their gravity, and then kept going out toward interstellar space. Today, it sits roughly 16 billion miles from Earth, around 26 billion kilometers away, which is almost one light day of distance. Light needs about a day to cross that gap. Voyager needed close to 5 decades. That's the scale mismatch you're dealing with. Half a human lifetime at real rocket speeds has bought us one single day of light travel distance. Now apply that to your own life. If you spent 80 years moving at Voyager speed, your total gain would still only be a few light days. You don't get anywhere near a light year, and a light year is the minimum unit that really matters once you step outside the solar system. So just stretching out the mission time by itself doesn't solve the problem. Long missions plus slow ships still add up to almost nothing on interstellar scales. So the basic numbers are now on the table. Light could cover 80 light years in your lifetime. Our fastest probe would need more than 1,000 years to cross 1 light year. Our longest running probe has taken almost 50 years to get to 1 light day. When you line those up, you can ask the real question clearly. When people ask, how far could a real human really travel in one lifetime, what they're actually asking is, given realistic engines, realistic fuel, and the limits of human biology, how much of the universe can you personally cross before your body gives out? You have to survive acceleration. You have to carry or receive enough energy to speed up and slow down. You have to shield yourself from radiation, and you have to bring life support that keeps working for decades. All of that costs mass and complexity, and every extra pound you carry makes it harder to go fast. This turns your lifetime into a very specific optimization problem. Push for higher speed, you need more energy and fuel, and your ship gets heavier. Try to cut mass, you lose redundancy and comfort, and the mission becomes more dangerous. Try to extend mission time, your life support and human factors start to break down. Somewhere inside those trade-offs, there's a maximum practical distance that one human or one crew can cross between birth and death. It won't be anywhere near the size of the galaxy. It won't even be a big chunk of the local region. But it might, with the right technology, be just enough to reach another star. So this episode is going to walk that line all the way out. You're going to start from the surface of Earth, fight your way through the speed barriers around our planet, step into the inner solar system, push out past the giant planets into deep space, and ask at every level, does this distance still fit inside one human life? By the end, you'll have a hard answer, not a fantasy, about whether you could ever stand under another sun, or whether your entire life is forever locked inside a tiny bubble around the one star you were born next to. Here's the next question you need to face. Before you think about Mars, Jupiter, or any star at all, how much of your lifetime do you have to spend just to break free from Earth in the first place? How much of your lifetime do you burn just to stop Earth from pulling you back down? To start real space travel, you have to pay a hard entry fee called escape velocity. Earth's gravity is strong enough that if you want to leave for good, you need to reach a speed of about 25,000 miles per hour, roughly 40,000 kilometers per hour. That's the speed you roughly cancel the pull of the planet. Go slower than that and you fall back. Hit that speed or more and you're no longer bound to Earth. You can't reach that with planes or jets. You need a rocket that turns huge amounts of fuel into thrust in a very short time. That's why the rockets that matter here are vehicles like Saturn V, Falcon 9, and the Space Launch System. Saturn V, which sent Apollo crews to the moon, burned millions of pounds of propellant in just a few minutes, peeling off stages as it climbed. Falcon 9 and Falcon Heavy do the basic trick with modern engines, and SLS is designed to throw heavy payloads toward the moon and beyond. Everything you see on the launch pad, all that hardware and fuel, is there just so a tiny capsule or probe can reach the speed it needs to not fall back to Earth. So after you light that fuse, ride through G-forces and shut off the engines, where are you really in cosmic terms? Most of the time, the answer is low Earth orbit, which is still basically home. The International Space Station flies at an altitude of only about 250 miles, or 400 kilometers above the surface. Earth is about 8,000 miles, or 13,000 kilometers across, so the station is just a tiny step above the surface. Up there, you circle the planet in around 90 minutes, moving at roughly 17,500 miles per hour, or 28,000 kilometers per hour. You see rapid sunrises and sunsets. You look down and see continents and oceans in one glance. But the truth is, you have barely left. You are skimming the top of the atmosphere, still deep in Earth's gravity well. This is the first uncomfortable point in your journey. You can spend money, huge engineering effort, and risk human lives, and at the end of it, you are still sitting in a thin shell around Earth, not actually going anywhere across the solar system. Low Earth orbit is not travel. It is parking at the edge of the planet. So, what changes when you decide you do not just want to orbit, you want to go somewhere, to the moon or to Mars? To leave Earth's neighborhood, you need more than orbit speed. You need a transfer burn, what mission planners call an injection. For the Apollo missions, once the spacecraft reached Earth orbit, a third-stage engine fired again to perform a translunar injection burn. That pushed the spacecraft to a velocity of around 24,500 miles per hour, or 39,400 kilometers per hour, relative to Earth, enough to climb out of Earth's gravity and intersect the moon's orbit. Even then, the trip took about 3 days to cover the roughly 240,000 miles or 384,000 kilometers between Earth and the moon. On the cosmic scale, that distance is tiny, and the speed is still nowhere close to what you would need for interstellar travel. Mars missions work on similar principles, but with bigger numbers. Spacecraft headed for Mars leave Earth on a curved path around the Sun, a transfer orbit that lines up with where Mars will be months later. Departure speeds are again in the range of tens of thousands of miles per hour, but the distances are larger. At a good alignment, called opposition, Mars can be about 140 million miles, or 225 million kilometers, away from Earth. Crossing that gap with current technology means 6 to 9 months of coasting flight, letting the sun's gravity bend your path. You are not thrusting the whole way. You do a big burn near Earth, then let orbital mechanics carry you the rest of the distance. At this point, you might ask, why not just build bigger rockets, load more fuel, burn harder, and get there faster? Here is where the fuel reality check hits. Rockets are ruled by a relationship engineers call the rocket equation. To get more speed, you have to throw more propellant out the back of the rocket. That means you need to carry more propellant at launch. But that extra propellant itself has mass, which makes the rocket heavier, which means you need even more propellant to accelerate the original propellant, and so on. This loop is brutal. In practice, most of the mass of a big rocket on the pad is just fuel and structure to lift that fuel. So when you say, just go faster, you are really saying launch a much larger, more expensive rocket, mostly full of even more fuel, just to squeeze out a modest increase in final speed. Very quickly, this becomes impractical, especially for crewed missions where you also need life support, radiation shielding, and the safe structure for humans. The rocket equation is the first hard limiter that tells you, no, you cannot simply stack more fuel forever and expect to reach a useful fraction of light speed. So after all that effort, all that fire, all those tons of propellant turned into exhaust in a few minutes, what have you actually achieved in terms of going far? You have reached the thin shell around Earth, or at best, you have taken a shot to the moon or set yourself up for a months-long cruise to Mars. In the scale of the universe, this is still step zero. The distance from Earth to the moon, 240,000 miles or 384,000 kilometers, is tiny compared to the 93 million miles between Earth and the Sun. And both of those are nothing compared to the 25 trillion miles to the nearest star. You have burned through a huge amount of hardware and fuel, and you've only just started to move away from the planet you were born on. That raises the next hard question. If escaping Earth and making short trips to the moon or Mars already consume this much energy and engineering, what does that say about your chances of touring the entire inner solar system within a single lifetime? How big is the space you are actually trying to cross when you say inner solar system? Start with one basic unit, the distance from Earth to the Sun, called 1 astronomical unit, or 1 AU. That's about 93 million miles, around 150 million kilometers. Light moving at 860,000 miles per second, or 300,000 kilometers per second, takes about 8 minutes to cross that gap. That means when you look at the sun, you're seeing it as it was 8 minutes ago. Now compare that to what your ships can do. A real ship running on chemical rockets needs months to travel a single AU on an efficient path. So just to cross the Earth-Sun distance, light needs minutes. You need a big launch, careful planning, and a huge chunk of a year. Now zoom out a bit and look at the layout of the inner planets themselves. Mercury orbits the Sun at about 0.39 AU, so roughly 36 million miles or 58 million kilometers from the Sun. Mars orbits at around 1.5 AU, about 140 million miles or 225 million kilometers from the Sun. Venus sits at about 0.72 AU. None of these numbers are crazy big yet, but remember, you are not jumping across these distances in straight lines. Every trip is curved, following orbits around the Sun, timed so that the target planet is in the right place when you arrive. For Mars, that turns into typical mission profiles, where you leave Earth, fire your engines to enter a transfer orbit, and then coast for 6 to 9 months to intercept the planet. Your speed during that cruise is usually in the range of tens of thousands of miles per hour, which sounds fast, but across these millions of miles, it still adds up to a long, slow drift. Mercury and Venus missions use different paths and gravity assists, but the same principle applies. You are always trading time for fuel, moving at speeds that are impressive for engineering, but small compared to the scale of the solar system. So what does that mean for you personally, if you are not just a passenger on one mission, but someone trying to spend a whole career exploring this inner zone? Say you manage to have about a 40-year active astronaut career, starting in your late 20s and going into your 60s or so. In a very optimistic near-future scenario, you might fly several major missions. Maybe you go on a crewed mission to Mars, out for 6 to 9 months, stay on the surface for a while, then 6 to 9 months back. That single round trip could easily burn 2 to 3 years of your life from training through recovery. Add another Mars mission a decade later, maybe a long-duration mission to a near-Earth asteroid, maybe a Venus flyby, or a mission to a Mars moon like Phobos or Deimos. If you stack several of these, your total distance traveled over your entire career might reach a few billion miles, a few billion kilometers, counting all the loops around the Sun and the transfers between planets. On a human scale, that is enormous. You will have crossed more distance than every commercial flight you could ever take in your life combined. You will literally have moved billions of miles away from the place you were born and come back alive. But on the scale of the solar system, you are still deep inside the Sun's immediate neighborhood. You are moving within a narrow band from about 0.4 AU to maybe 1.5 AU, staying inside a bubble of a couple of 100 million miles around the Sun. You are nowhere remotely close to the outer planets. You have not approached the edge of the Sun's influence, and you are nowhere near another star. Your entire 40-year high-intensity, high-risk career is a detailed exploration of what is essentially the inner few percent of the solar system's radius. You might ask again, why not just decide that this is too slow, design a ship with more thrust, and cut those Mars trip times way down? Here's the next constraint. To change your speed in space, you talk about delta V, the change in velocity you can produce with your engines. The kinetic energy needed to give your ship a certain speed grows with the square of that speed. In plain language, if you want to double your speed, you do not just need twice the energy, you need roughly 4 times the energy. If you want to triple your speed, you are suddenly asking for 9 times the energy. That's before you even factor in the mess of carrying propellant. Because your ship carries its propellant, more delta V means more propellant mass. More propellant mass means a heavier ship at launch. A heavier ship needs even more thrust and more propellant to reach orbit and then to push harder in deep space. On top of that, higher burn rates and higher speeds mean more heat to manage, more stress on your engines, and more difficulty keeping your crew safe. Very quickly, chemical rockets hit a practical wall. You can push trip times down from, say, 9 months to maybe a few months with extreme engineering and risk, but you don't get an order of magnitude improvement without leaving chemical propulsion behind. You can see this limit already in the missions we have flown. New Horizons, the probe that went to Pluto, is a good example of how far you can push even with careful planning. It left Earth on one of the fastest escape trajectories ever flown, used a gravity assist at Jupiter to boost its speed, and still took about 9.5 years to reach Pluto at roughly 3 billion miles, 5 billion kilometers, from the Sun. For inter-system missions, NASA and other agencies are planning things like Mars Sample Return, which chains together multiple launches and vehicles over many years just to grab a few pounds of Martian rock and bring it back. Crewed Mars mission designs involve huge rockets, orbital assembly, and long surface stays because the costs of fast out and back trips are so high. So even when you plan well, use gravity assists, and run your engines as hard as safety allows, inner solar system travel stays in the months to years per trip regime. That's the reality of chemical propulsion and the energy demands of moving real mass between planets. Now line that up with your 80-year life. In the best realistic case, you spend maybe a few decades flying missions. You can rack up a few billion miles. You can touch Mars. You might see Venus close up. You might work near an asteroid. You get a detailed tour of a small band around the sun, but you don't escape it. Your entire timeline is already mostly gone, and you have never been farther than a couple of AU from the star that set the rules for your orbit. That brings you to the next harsher step in this story. If the inner solar system already consumes years of travel time and the best part of a human career, what happens when you try to go beyond Mars and the asteroid belt, out to Jupiter, Saturn, Uranus, and Neptune, where the distances explode and the travel times start to swallow entire decades? How long does it actually take not to leave the solar system, but just to reach the big planets sitting farther out from the sun than Mars? Start with Jupiter and Saturn, because they're the first major test of how large our own backyard really is. Jupiter orbits at about 5.2 astronomical units from the Sun. That's more than 5 times the Earth-Sun distance, so around 480 million miles, roughly 780 million kilometers, from the Sun on average. Saturn sits even farther out at around 9.5 AU, close to 880 million miles, about 1.4 billion kilometers from the Sun. When you fly from Earth to these worlds, your paths are curved, your targets move, and your travel times stretch into years, even for fast robotic probes. Voyager 1 is a good benchmark here. It launched in 1977 on a highly efficient path using a rare alignment of the outer planets. From launch, it took about 2 years to reach Jupiter. That is already longer than a crewed mission to Mars would take. Then, it needed about 4 years total from launch to reach Saturn. The probe was not crawling, it was moving at tens of thousands of miles per hour, and it was using gravity assists to boost its speed. Even so, crossing just the inner part of the outer planet region took years of continuous flight. So from your perspective, even with aggressive, well-planned trajectories, the first gas giant takes you a couple of years to reach. The second takes several years, and you are still nowhere near the edge of the solar system. You have only moved out to around 10 AU at Saturn, while the sun's influence extends much farther. Now look at a more extreme case, Pluto and the New Horizons mission. Pluto orbits in a stretched elliptical path, ranging roughly between 30 and 49 AU from the Sun. That means its distance can be anywhere from about 2.8 billion to over 4.5 billion miles, around 4.5 to 7.5 billion kilometers. New Horizons launched in 2006 on one of the fastest escape trajectories ever achieved by a spacecraft. It then used Jupiter for a gravity assist to gain even more speed. After that, it coasted almost the entire rest of the way. Even with that aggressive plan, it took about 9.5 years to reach Pluto, and the distance at encounter was about 3 billion miles, around 5 billion kilometers from the Sun. So almost a decade of flight at very high speeds for a one-way high-speed flyby of a dwarf planet at the edge of the classical planets. Now put yourself in that picture. Say in some future, humans build a crewed ship that can roughly match Voyager-class trajectories or better. What does a grand tour of the outer giants look like for you in terms of your lifetime? You would launch from Earth, spend years cruising to Jupiter, maybe around 2 years if you match Voyager scale. You could do a close pass, drop into orbit, or skim the system for a while, but any serious exploration there already eats into your clock. Then, if you boost out to Saturn, you're looking at least a couple more years of cruise, depending on your exact path and propulsion. Add real dwell time in each system, time for science, time for safe orbital maneuvers, and you are stacking years quickly. If you then try to push onward to Uranus and Neptune, the time hit becomes even worse. Those planets orbit at about 19 and 30 AU from the Sun. Each transfer between them can cost you many more years. A realistic crewed grand tour, even with optimistic engineering, starts to look like a multi-decade odyssey. You could launch in your 20s, visit Jupiter and Saturn in your 30s, maybe Uranus in your 40s, maybe Neptune in your 50s, and by the time you're thinking about the edge of the sun's influence, you're late in life, with your health, your ship, and your systems all aging along with you. In that best-case aggressive scenario, how much distance have you actually crossed? You might have made it out to a few dozen AU, maybe 30, 40, possibly more if the mission is extremely ambitious. That is tens of Earth-Sun distances, which sounds large, but compared to what's around you, it's still only a fraction of the full reach of the Sun's domain. To see that clearly, you have to talk about the heliosphere, the vast bubble carved into interstellar space by the sun's solar wind. The heliopause, the rough outer boundary of this bubble, is where the solar wind's pressure drops enough that the interstellar medium pushes back. This boundary sits at around 120 AU from the sun, though it's not a perfect sphere and can vary. Voyager 1 crossed this boundary in 2012, after decades of travel. Look at its numbers. After a gravity assist boost from Jupiter and Saturn, Voyager 1 has been moving at about 38,000 miles per hour, around 61,000 kilometers per hour, which translates to roughly 3.6 AU per year. In simple terms, it crawls across the solar system at a few Earth-Sun distances per year, and that's enough to give it the distance record. Now, scale that motion to your life. Take a human lifetime of about 80 years and ask if you could ride alongside Voyager at its current pace, what size of space could you personally cross between birth and death? At a few AU per year, you're looking at something like a few hundred AU at most over 80 years. To keep it simple, even if you round it way down and just say a few dozen to a few hundred AU, that still builds a bubble with a radius of maybe a few billion to a few tens of billions of miles around the sun. On a human level, that's gigantic. That's far beyond all the planets you've ever heard of in school, out into a region most people never even think about. But compared to the galaxy, that bubble is microscopic. The sun itself is about 93 million miles, 150 million kilometers from Earth, just 1 AU. The region out to a few hundred AU is a tiny speck compared to the separation between stars. If you represented the distance to the nearest star as the length of a football field, your Voyager-sized lifetime bubble would be like a few grains of dust near the goal line. You can move a long way relative to Earth, but relative to the Milky Way, you have barely started to move at all. To see how harsh that is, you have to put Voyager's record up against the real interstellar target. Take Proxima Centauri, the closest known star to the Sun. It is about 4.25 light-years away. In miles, that is around 25 trillion miles, roughly 40 trillion kilometers. Compare that to Voyager's 16 billion miles. You're short by a factor of more than 1,000. If you tried to cover the distance to Proxima at Voyager's 38,000 miles per hour, you're looking at a travel time of over 70,000 years. That is not one lifetime. That is about 1,000 lifetimes stacked end to end, assuming 70 to 80 years per person. If you launched the ship at that speed, back when the first cities on Earth were just forming, it would still have tens of thousands of years left to go. This is the key point, and it is not abstract. Voyager 1 gives you a real measured data point for what long-duration travel looks like using current-type propulsion. It has survived for decades in space, outside Earth's protective magnetic field and atmosphere. It has flown beyond the major planets, across the outer solar system, and has now crossed a heliopause into interstellar space. It is still sending back data on charged particles, magnetic fields, and the structure of that boundary region. That proves something important. You can build machines that work for many decades in deep space. Electronics can survive. Power systems can limp along. Communication can happen across tens of billions of miles. But Voyager also shows you in a very blunt way how slow we are. After almost 50 years of flight, it has covered a distance that light crosses in about 1 day, and it has only moved a tiny fraction of the way to the nearest star. If you compare its current distance to the 25 trillion miles to Proxima Centauri, it has covered well under 1,000th of that gap. You can think of it as drawing a tiny scratch at the very inner edge of the map between stars. That is the performance of our Champion probe. Now bring this back to your 80-year life. If your entire lifespan matched Voyager's pace, you would not even get close to a single light year. Your path would stay inside a minuscule slice of the local region around the sun. You could break free of Earth, pass beyond the orbit of Neptune, cross the heliopause, and float in interstellar space, and you would still be stuck in the sun's immediate neighborhood. The nearest star would not just be out of reach, it would be out of reach by such a huge factor that your personal travel distance almost rounds down to zero on that scale. That is why in this story, Voyager matters so much. It is not just a nostalgic old probe sending scratchy data from the edge of the solar system. It's a real test of what our current propulsion and engineering can do over a time frame comparable to a human life. It shows that we can keep hardware alive, we can keep it flying, we can cross large parts of the solar system, and at the same time, it shows that with rocket technology in the same class, your lifetime buys you almost nothing in interstellar terms. It's a reality check against all the casual talk of star travel as if it were just a longer version of going to Mars. So you can sum it up like this. Voyager is our champion marathon runner, and it proves that with today's kind of propulsion, your entire lifetime barely buys you a single step toward another sun. That raises the next, sharper question. If endurance alone is not enough, and Voyager's slow marathon only gets you a tiny scratch on the interstellar map, what happens when you push for raw speed instead, and look at the one probe that has gone faster than anything else humans have ever launched? Parker's solar probe shows you what happens when humans push for raw speed as hard as current technology allows, and the result is both impressive and depressing at the same time. Start with the basic numbers, because they matter. Parker Solar Probe is a small, uncrewed spacecraft flying repeated close passes around the sun. On its fastest dives, it has reached about 430,000 miles per hour, roughly 690,000 kilometers per hour. Break that down and you get something like 125 miles per second, about 200 kilometers per second. Nothing else humans have ever built has moved that fast under its own momentum. Not a rocket, not a plane, not any previous probe. In terms of raw speed, Parker is the current record holder. That sounds like it should change everything, right? Hundreds of thousands of miles per hour, a speed that would carry you around Earth in minutes and across the Earth-Moon distance in less than an hour. So here's the next question. If you take that speed and put it next to the speed of light, does it finally look like you're in the same league, or are you still stuck at the bottom of the scale? As soon as you compare Parker to light, the situation collapses. Light moves at about 186,000 miles per second, around 300,000 kilometers per second. Parker's 125 miles per second is only about 0.064% of that, roughly 6/100ths of 1%. Put differently, if light is the full 100%, Parker barely gets you past 0.06%. It is still stuck in the tiny fraction zone. If you try to cross a single light year at Parker's top speed, you're looking at more than 1,500 years of travel time. Your 80-year life covers only 1/20th of that. So even with the fastest probe we've ever built, a 1 light-year crossing is still way beyond the human lifespan. That leads to the obvious next thought. If Parker can move that fast near the sun, why not just copy that speed profile for a starship? Why not say, okay, we are at 0.064% of light speed already, let's scale that up, make it crude, and go interstellar? Here is the problem. Parker does not reach those speeds by pure engine power alone. It gets there by diving deep into the sun's gravity well, falling inward and converting gravitational potential energy into kinetic energy. The spacecraft starts on a path that takes it closer and closer to the sun with each orbit, using Venus gravity assist to adjust its trajectory. As it falls toward the sun, it accelerates, just like a ball rolling downhill, only in 3 dimensions around the star. That is why its peak speed happens at perihelion, its closest approach to the sun, not out in empty space. You cannot use that same trick to cruise between stars. There is no giant downhill slope that you can just roll down indefinitely in interstellar space. Gravity assists work when you are near massive bodies, like planets or a star, and they mostly change your direction and speed relative to those bodies. Once you're far from everything, in the deep gap between stars, you're on your own. To maintain Parker-level speeds in that environment, you would need propulsion systems that can pump enormous amounts of energy into your ship, accelerating you to that speed and then either holding it or reboosting you as you lose speed due to tiny interactions with gas, dust, or any braking you choose to do. So just go Parker everywhere really means have engines and fuel or beamed power capable of pushing a large crewed vehicle up to 430,000 miles per hour and keeping it there, not for minutes near a star, but for decades in empty space. That is an energy problem on a completely different level than what Parker's dealing with. Then there's the environment Parker flies through, which is hostile even for a small robotic probe. Near the sun, the spacecraft faces intense heat and radiation. To survive perihelion, it uses a carbon-carbon composite heat shield that can withstand temperatures above 2,500 degrees Fahrenheit, about 1,370 degrees Celsius, on the sun-facing side, while keeping the instruments in its shadow at much lower temperatures. That is already a major materials achievement. The shield has to handle repeated heating and cooling cycles, high radiation, and the dynamic stresses of fast flight. Now, imagine you try to send a crewed ship through similar conditions just to get a speed boost, or try to move at Parker-like speeds through interstellar space. A human-rated craft would need not only a heat shield, but full thermal control for a large interior volume, plus shielding against radiation and high-speed particle impacts. Out in interstellar space, even tiny grains of dust become serious threats at these velocities. A dust particle the size of a grain of sand hitting your hull at hundreds of thousands of miles per hour carries enough kinetic energy to do serious damage, like a small explosive. Even micron-scale particles can erode surfaces over time, so your ship needs thick shielding up front, maybe layered Whipple shields, maybe ice, maybe magnetic fields, all of which add mass, and mass is your enemy when you want high speed. This is the bind you're in. To move at Parker speeds with humans on board, you need massive shielding and a robust structure which makes your ship heavy, which demands more energy and bigger propulsion systems, which in turn introduce more heat and structural load problems. With a tiny robotic probe that can tolerate extreme conditions and has no living passengers, you can accept risks and constraints that you simply cannot accept for a human crew. So, what does Parker really tell you about your lifetime and the upper limits of travel? It tells you that even the fastest object humans have ever built only reaches a tiny fraction of light speed. It shows you that to even scratch that fraction, you need to play games with gravity, fly close to a star, and engineer specialized shielding. It hints at the kind of energy you would need if you ever wanted to sustain those speeds without help from a gravity well. And it shows that converting that kind of environment into something safe enough for humans is not a small upgrade. It's a major jump in difficulty, in mass, and in engineering complexity. In other words, Parker proves that breaking into the hundreds of thousands of miles per hour club is possible for robot probes, but turning that into a practical, safe, crewed starship is a different problem entirely, not just add chairs and oxygen. Our fastest probe is a demonstration of the scale of the challenge, not a ready-made template for human interstellar travel. So you now have both sides of the picture. Voyager shows you what decades of steady travel look like at modest speeds. Parker shows you what extreme speeds look like for short periods near a star. But together, they both point to the same conclusion. With today's style of propulsion, your lifetime is nowhere near enough to cross the gulf between stars. That brings up the next critical question. If even our best speeds are that tiny compared to light, what actually happens when you put those numbers next to the true distances between stars and you stop thinking in miles and start thinking in light years? So what actually changes when you stop thinking in miles and start thinking in light years? The first thing that hits you is the size of the basic unit. 1 light year is the distance light travels in 1 year, moving at about 186,000 miles per second, around 300,000 kilometers per second. When you turn that into a number, you get roughly 5.88 trillion miles, about 9.46 trillion kilometers, for just 1 light year. That's your new ruler once you step outside the solar system. And the nearest real targets are already several of these units away. Proxima Centauri, the nearest known star to the Sun, sits at about 4.24 to 4.25 light years away. Alpha Centauri A and B, the brighter binary pair in the same system, are around 4.35 light years away. So the nearest interesting place is not a few billion miles away, it's more like 25 trillion miles, about 40 trillion kilometers out. Now compare that to the space you've been talking about so far, the solar system. The orbit of Neptune, the outermost major planet, is at about 30 astronomical units from the Sun. 1 AU is the Earth-Sun distance, about 93 million miles, around 150 million kilometers. So Neptune's orbit has a radius of roughly 2.8 billion miles, about 4.5 billion kilometers. When you put that next to 25 trillion miles to Proxima Centauri, you see the gap. In AUs, Proxima's more than 260,000 AUs away. Neptune is at 30 AUs. The entire planetary system you think of as big is a tiny dot at the center of a huge empty sphere. Once you zoom out to the scale of nearby stars, your whole planetary neighborhood really does shrink into something that feels like a pinprick. So the obvious next question is, with the speeds we've already talked about, how long does it actually take to cross that gap? Take Voyager 1 speed first, because it's a clear, real number. Out in interstellar space, it moves at about 38,000 miles per hour, around 61,000 kilometers per hour. That's good enough for roughly 3.6 AUs per year. When you do the time estimate to Proxima Centauri at around 4.25 light years, you get a number on the order of 73,000 years. That's how long it would take to cover about 25 trillion miles at Voyager's pace. That's not just beyond your life, it's beyond your civilization's lifetime as you know it. 73,000 years ago, humans were still in the deep Stone Age. Now switch to Parker Solar Probe's record speed, roughly 430,000 miles per hour, about 690,000 kilometers per hour. That is around 0.064% of light speed. It is more than 10 times faster than Voyager. That sounds like it should fix the problem, but it does not. At that speed, you are still looking at something like 7,000 years to reach Proxima Centauri. You can see the pattern. Jumping from 40,000 miles per hour to 400,000 miles per hour knocks the travel time down by about a factor of 10. But you are still thousands of years away from the nearest star. These are not tweaks you can squeeze into a human life. They are timescales that swallow entire cultures. Now put yourself directly into that picture. Say you somehow launch at birth and spend your entire 80-year life on a ship. You never stop, you never come back, you just go. At sub-relativistic speeds like Voyager or even Parker, your personal progress across that 4.25 light-year gap is tiny. At Voyager speed, 80 years is nothing against a 73,000-year trip. You would cover about 1,000th of the total distance. At Parker speed, 80 years is still nothing against 7,000 years. You would cover roughly 1/11th of the way there. You die, and you have not even cleared a single light year. This is the key point, and it is the first real hard wall you hit when you talk honestly about going to another star in one human lifetime. If you stay in the speed range we know how to reach with rockets and gravity assists, even when you push the upper limit, you simply do not get there. The math does not care how determined you are or how advanced your light support is. Sub-relativistic velocities, meaning speeds that are still a tiny fraction of light speed, only buy you a small slice of the distance to the nearest star before your biological clock runs down. So when people say, could we actually reach another star with a crew in a single human life, the hidden requirement is this. You have to start talking about significant fractions of light speed, not 0.06%, but 10%. 50%, 90% of light speed. And once you go there, relativity shows up. Time dilation starts to matter. Your time on the ship slows down relative to time back on Earth. From your point of view, the trip might fit inside a few decades, but from Earth's point of view, more time has passed. That creates a different kind of trade. You can make the journey fit into one subjective lifetime on board, but you pay for that by being out of sync with the world you left behind. The other option is to accept that the people who arrive are not the ones who launched. That is the generation ship concept. You launch a large habitat, your children grow up on board, their children do too, and many generations later, the descendants reach the target system. Each individual still only gets 70 or 80 years, but the ship as a whole spans thousands of years. That solves the total travel time problem, but it breaks the original question, because no single person actually lives to see both departure and arrival. So you reach a harsh conclusion. If you stay with speeds in the Voyager or Parker range, your personal lifetime is effectively useless for interstellar travel. If you want a single human to launch from near Earth and actually arrive at another star before they die, you need engines that push you into fully relativistic territory, with all the physics, energy demands, and survival problems that come with that. Without that, you are stuck in a situation where once you zoom out to interstellar scales, your lifetime basically collapses into a rounding error. That brings up the next big question you have to face. If chemical rockets and gravity tricks are not enough, and these interstellar distances destroy normal mission plans, is there any kind of propulsion, even in the next century category, that can realistically change your reachable distance inside one human life? Or are you permanently locked to a tiny bubble around the sun? Right now, the limit is clear. With chemical rockets, you do not get anywhere near another star in one lifetime. So the next question is simple. What if you switch to propulsion that is actually better than chemistry? Not magic, just the next step up. Start with nuclear thermal rockets, because they're the closest to something we could really build. Instead of burning chemical fuel like hydrogen with oxygen, you run hydrogen through a nuclear reactor. The reactor heats the hydrogen to extreme temperatures and you blast that hot gas out the back. Because the gas gets hotter, it leaves the engine faster, and that higher exhaust speed means better performance. In plain terms, a good nuclear thermal rocket might give you roughly 2 to 3 times the efficiency of a chemical rocket. That translates to 2 to 3 times the useful change in speed for the same fuel mass. What does that do to trip times? It doesn't give you miracles, but it helps. Months to Mars could become weeks. Multi-year trips to Jupiter could be cut down to many months. Inside the solar system, that matters. You spend less of your life coasting and more time at the destination. Then there's nuclear electric, where you use a reactor not to heat propellant directly, but to generate electricity. That power then feeds electric thrusters, like ion drives or Hall effect thrusters. This blends into the second big category, ion and electric propulsion. These engines already fly. Missions like Dawn and Bepi-Colombo use ion thrusters that eject ions, charged particles, at very high speeds, tens of miles per second, tens of kilometers per second. That exhaust velocity is far higher than what chemical engines produce. The trade-off is that the thrust at any moment is tiny, like the weight of a sheet of paper in your hand. But you can keep that tiny push running for months or years. Over long times, that gentle shove adds up. A spacecraft with an ion drive can slowly spiral outward, changing its orbit bit by bit, and eventually reach high speeds compared to where it started. You don't get anywhere close to light speed, but you can beat chemical rockets by large factors when you look at total delta V over emission. For you, that means a future where robotic probes and maybe even crewed cargo tugs use electric propulsion to move things around the inner and outer solar system more efficiently. Travel times shrink by factors, not by orders of magnitude, but enough that complex logistics across the planets become possible. Now step up to something more aggressive. Fusion propulsion. Here you're not talking about just heating gas or pushing ions with solar panels, you're trying to tap the same process that powers stars. Classic studies like Project Daedalus imagined a huge vehicle that carries frozen fusion fuel pellets. These pellets are fired into a reaction chamber and ignited behind the ship, and the reaction products blast out the back, pushing the ship forward. On paper, designs like that can reach perhaps 10 to 20% of light speed, so about 0.1 C to 0.2 C, if you solve a long list of engineering problems. At 0.1 C, about 1/10 light speed, the numbers finally start to line up with a human life. Proxima Centauri at around 4.25 light-years would then be roughly 40 to 45 years in Earth frame time, depending on how you accelerate and brake. If you launched as a young adult, say in your 20s, you might arrive in your 60s. That is still a brutal, decades-long mission, and it assumes everything works perfectly, from the engines to the shielding to the life support. But for the first time, you're talking about a single person having at least a theoretical shot at reaching another star before they die, not in thousands of years, but in one long lifetime. Beyond fusion, you get into antimatter and beamed propulsion. Antimatter rockets look amazing on paper because when matter and antimatter meet, they annihilate and release energy with incredible efficiency. You get far more energy per pound of fuel than with any chemical or nuclear reaction. That could, in theory, push a ship to very high fractions of light speed. The problem is production and storage. Right now, we can only make antimatter in labs in microscopic amounts, nanograms, and it takes huge energy to do it. Storing it safely, without it touching normal matter and blowing all that energy at once, is its own nightmare. So antimatter drives are not completely fantasy, but they are very, very far from practical. Beamed propulsion, like laser-pushed light sails, takes a different angle. Instead of carrying all your fuel on the ship, you leave the power source at home. A giant laser array on or near Earth fires a powerful beam at a large, thin sail attached to a probe. The beam's light pushes on the sail and accelerates the craft. Concepts like Breakthrough Starshot talk about gram-scale probes, tiny chips with sails, being pushed up to around 0.2 C, about 20% of light speed. At that speed, those tiny probes could reach Proxima in something like 20 years. For robots, this is huge. For humans, it is not directly useful yet because scaling up from gram-scale sails to massive crewed ships is not just a small upgrade. It is a completely different problem in terms of power, beam control, and sail strength. So where does all this leave your lifetime and your distance budget? The honest answer is that all of these systems are, at best, mid-future technologies. Nuclear, thermal, and ion propulsion are close, and versions of them exist already. Nuclear electric for large crewed ships is hard, but not crazy. Fusion drives, antimatter rockets, and true relativistic beam sails for anything larger than a tiny probe are still on the far edge of what we can even engineer on paper. But they are not pure fantasy like warp drives or hyperspace. They are hard physics and hard engineering, sitting in the zone of maybe in the next century or two if we really commit. These possible systems set the upper realistic bound for how far a single human might travel in one lifetime. With nuclear and electric propulsion, you can fully own the solar system, inner and outer, within decades. With a working fusion starship at around 0.1 C, you push your personal frontier out to a small bubble of nearby stars over 40 to 60 years. With something even closer to 0.5 C or 0.9 C, plus relativistic effects, you start to turn your 80 years into tens of light years of reachable distance, at least in your own frame of reference. And that raises the next key issue you cannot dodge. Once your ship starts moving at a serious fraction of light speed, your time on board and Earth time no longer match. So if you want to know how far your lifetime really stretches when you punch into those high speeds, you have to bring relativity into the story and ask, how much extra distance does time dilation actually buy you before your body still hits its hard 80-year limit? Relativity is where the rules of the game finally bend in your favor, but they charge you a price you probably do not want to pay. The core idea is simple. As your ship's speed gets close to the speed of light, your time and Earth's time stop matching. From your point of view on the ship, your clock looks normal. Your heart rate is normal, your aging feels normal, but when you compare your clock to a clock back on Earth, less time has passed for you. This effect is called time dilation. The faster you go, the stronger it is. At around 90% of light speed, 0.9 c, your time runs roughly 2.3 times slower than time on Earth. That means for every year you live on the ship, more than 2 years pass back home. Push up to 99% of light speed, 0.99 c, and the factor jumps to about 7. 1 year for you is about 7 years for Earth. This is not a trick or an illusion. It is how space-time actually behaves when you move that fast. So what does that mean for how much distance your 80-year life can cover if you have a ship that can hit those speeds? Take a simple case. Suppose your ship reaches 0.9 c and cruise for a long stretch at that speed. If you do that for 40 years by your onboard clock, you travel about 36 light years as measured in the frame of the galaxy. That's 36 times the 5.88 trillion miles, 9.46 trillion kilometers that define a light year. From your point of view, you've spent 40 years in flight. From Earth's point of view, more than 90 years have gone by because of that factor of about 2.3 in time dilation. You're still a normal human with a normal feeling lifespan, but your path through space is now dozens of light years long. Now look at 0.99 c. At that speed, time dilation is strong. Your time is slowed by a factor of about 7 relative to Earth. If you again spend 40 years of ship time cruising, you will have traveled roughly 40 light years, and several hundred years will have passed on Earth. So in your own experience, you left at age 20, you arrive at age 60, and the distance you have crossed is on the order of 40 light years. For people back home, you launched in their 2100s and arrived in their 2400s, or something in that range. Your life fits inside a normal human span, but you have stretched that span across a big chunk of the local stellar neighborhood. Reaching those speeds, though, is not something you do with one big rocket burn and some wishful thinking. You have to think about acceleration in a way that your body can actually survive. Your body can tolerate about 1 g for long periods, which is the same acceleration you feel right now from Earth's gravity, about 32 feet per second squared, or 9.8 meters per second squared. If your ship accelerates at around 1 g in the forward direction, you feel gravity as if you were standing on a floor. That is comfortable for months and years, and it gives you artificial gravity for free. With a constant 1 g push, your speed ramps up fast. In about a month or a little more, on the order of 35 days of continuous 1 g thrust, you can reach around 0.1 c, 10% of light speed. Keep pushing for several months, and you can get to around half the speed of light, 0.5 c. Keep going longer, up to about a year of continuous acceleration, and you can approach relativistic speeds like 0.9 c. Then you have to flip the ship and brake at 1 g for another block of time, so that you do not arrive at your target still screaming through space at near light speed. All of this assumes you have a propulsion system with insane amounts of fuel or access to a powerful external energy beam, like a gigantic laser pushing you, and that your engines are efficient enough to keep that 1 g thrust going for months at a time. With chemical rockets, this is impossible. With advanced fusion or beamed propulsion, it is at least something you can write down and analyze. If you accept those assumptions, where could you actually go in one subjective lifetime? Once you draw a sphere of about 30 to 40 light years around the sun, the map starts to look busy. Inside that radius, there are dozens of known stars. Some are single stars, some are binaries or triples. Many have detected exoplanets. Some of those planets sit in the so-called habitable zone, where temperatures could allow liquid water, depending on the atmosphere. At 0.9c to 0.99c, and with proper time dilation, you could design missions where a single human crew or even a single person launches in their 20s, accelerates for some months, cruises for a couple of decades, and then slows down and arrives in their 60s or 70s at a star tens of light years away. In terms of your own lifespan, you have turned the unreachable into reachable. You could even chain systems. With very aggressive planning, you might visit one star, spend a few years there, then accelerate again and head for another nearby star a few light years away. Your personal timeline might look like 10 years to accelerate and travel, a few years exploring, another 10 years to the next system, and so on. Over 40 or 50 ship years, your personal path could cross dozens of light years and touch multiple star systems. From your point of view, it is a long but continuous life, full of events and locations. From the galaxy's point of view, you have carved a narrow route through a crowded local neighborhood of stars. But here comes the twist you cannot dodge. Relativity is not free. The same time dilation that helps you pack more distance into your lifetime also stretches the gap between you and everyone back home. If you travel at 0.9c or 0.99c for decades, Earth does not wait politely. Decades for you are many more decades or even centuries for Earth. The world you left behind ages much faster than you do. Systems shift, languages change, technology jumps several generations, and entire cultures rise and fall while you're in transit. If you ever decide to turn around and come back, you face the same process in reverse. You accelerate, cruise, and decelerate again. By the time you step onto a station or a planet near the sun, you might have experienced, say, 60 to 70 years of life. But in the frame of Earth, hundreds of years might have passed. Everyone you knew is gone. The society you trained in and launched from is as old and distant as medieval history feels to you right now. You have used relativity to extend your reachable distance, but the cost is total separation from your original timeline. So, relativity gives you a real answer and a harsh one at the same time. Yes, if you can reach high fractions of light speed with a 1G capable engine and the right shielding, your personal lifetime can cover tens of light years. You can go well beyond the solar system. You can reach multiple star systems. You can live and die under alien suns. But the price is that you're effectively leaving your original civilization forever. From their point of view, you vanish into the future. From your point of view, they vanish into the past. And this still assumes you can survive the trip physically, because all these numbers about 0.9c and 0.99c quietly ignore one ugly fact. Moving that fast through real space filled with dust, gas, and radiation is not just a navigation problem, it's a constant threat to your ship and your body. So the next question is obvious and ugly. If you try to turn your lifetime into a high-speed crossing of tens of light years, what actually happens when every tiny dust grain in your path hits you like a bullet, and the space between the stars turns into an invisible sandblaster aimed straight at your hull? Once you start talking about flying at a big chunk of light speed, the space between stars stops being empty and starts being dangerous. The first problem is interstellar dust. Space is not a perfect vacuum. There are tiny grains of dust and gas everywhere. At airplane speeds, they do basically nothing. At 0.1c, 10% of light speed, they become weapons. A grain of dust the size of a grain of sand hitting your hull at a fraction of light speed carries kinetic energy on the level of a small explosive. It's like firing a high-velocity projectile straight into your ship. Even much smaller particles, things you would call microscopic on Earth, start to hurt you at 0.1c. Micron-sized bits of dust, just a few millionths of a meter across, can chip away at your shielding continuously over decades. You're basically sandblasting your own ship by flying through the interstellar medium. Now extend that over 20, 30, 40 years of flight. Every second, more tiny impacts. The front of your ship takes the worst of it. If your shield is too thin, it slowly erodes, cracks, and eventually fails. If your shield is thick, it can survive longer, but it weighs more, which makes the whole ship harder to accelerate. You're stuck in a constant trade between protect the crew and keep the mass low enough to reach the target before they die. Radiation is the next layer of trouble. On Earth, the planet's magnetic field and atmosphere protect you from most of the high-energy particles coming from the sun and from the galaxy. Once you are in deep space, those protections are gone. You are exposed to galactic cosmic rays, which are high-energy particles from supernovae and other violent events, and to solar storms, which can blast out intense bursts of particles. At normal interplanetary speeds, this is already a serious issue for long missions. You need shielding, storm shelters, and careful mission timing. At relativistic speeds, it gets worse. When you move very fast through a bath of background radiation and particles, the stuff in front of you gets blue shifted. In simple terms, the energy of particles and photons coming from the direction of your motion appears higher in your frame. That means more damaging hits per second at higher energies. Your effective dose of radiation from the front direction climbs. Instead of just worrying about random cosmic rays, you now have a boosted directional storm straight ahead. Keeping humans healthy for decades in that environment demands heavy shielding or clever field systems, both of which add complexity and mass. So you need shielding in front of you, thick enough to absorb constant dust impacts and persistent radiation, but not so massive that your engines can never push it to 0.5 C or 0.9 C. How do you even design that? Engineers have floated several ideas. One is a forward Whipple shield, which is a layered system of thin plates. The first layer breaks incoming particles into smaller fragments, which then spread out and are absorbed by deeper layers. Another concept is using magnetic fields or plasma shields to deflect charged particles, though those do less against neutral dust grains. You can also imagine sacrificial shields made of water or ice sitting in front of the main hull. The ice slowly vaporizes and erodes, taking the hits for you. All of these come with engineering nightmares. You have to manage heat, structural stress, erosion rates, and field stability for decades while your ship is traveling at a huge fraction of light speed with no external support. And remember, every pound of shielding you add is a pound your engines have to accelerate to relativistic speeds and then slow down again. If you double your shield mass to feel safer, you may have just pushed your mission from barely fits in a lifetime to arrives after the crew is dead. You cannot just say more armor without also saying more fuel, more power, more time. Navigation at these speeds is its own trap. At 0.5 C, half light speed, you are covering about half a light year every year of external time. Any serious hazard, a dense dust cloud, a rogue rock, even an unexpected concentration of smaller particles, needs to be detected years in advance, not days. Your sensors have to scan ahead, process the data, and give your guidance system enough time to make small course changes that, over long spans, shift your path by millions of miles. A tiny steering error at 0.5 C, left uncorrected, can put you millions of miles off target by the time you reach your destination system. If you're aiming for a planet or a tight orbital insertion, that's the difference between arriving and missing everything. At 0.9 C or higher, this precision requirement becomes extreme. Light from obstacles ahead takes time to reach you. By the time your sensor sees something, you're already much closer to it than you would be at slow speeds. Your reaction window shrinks. Automated systems have to act fast, long before human operators can debate options. Any software bug, sensor glitch, or miscalibration can turn into a lethal error when you're moving that fast. Diagnosing and fixing those problems mid-flight is not easy when your ship is also a closed ecosystem that has to stay stable for decades. Put all of this together and you see why these hazards are not just side issues. They directly limit how fast you can safely travel. It's not enough that your engine can, in theory, push you to 0.5 C or 0.9 C. You also need to survive every second at that speed. Dust, radiation, shielding mass, and navigation errors add up to a hard practical cap. At some point, you have to make a choice. You either cruise slower to reduce the impact energy of dust and the severity of radiation and navigation issues, or you risk a mission that might end in catastrophic failure long before the crew ever sees another star. And that choice feeds directly back into your core question. How far can you go in one lifetime? If survival demands that you cruise at, say, zero point 0.1 C instead of zero point 0.5 C, your reachable radius in 40 or 60 years shrinks dramatically. If you can never go faster than a certain safe speed because the environment becomes too lethal, then there's a hard ceiling on the distance any one crew can cover before age and biology stop them. So far, we've mostly talked about the ship as a machine: engines, shields, sensors. But you're not a probe, you're a living body inside that machine. And you're not traveling for hours or days, you're traveling for decades. That means turning your ship into a small, closed world that has to keep you alive the entire time. So here's the next question you need to face. Even if you solve propulsion and shielding, what happens when you actually count everything you have to bring with you, every drop of water, every breath of air, every meal, and realize that the mass of your own life support might be the biggest anchor holding you back from ever using your full speed? Once you move from how fast can the ship go to how long can humans stay alive on it, the problem changes completely, and it gets heavier in every sense. For a mission that lasts decades, you can't treat the ship like a plane that just carries enough fuel and snacks for a single trip. You need a closed-loop ecosystem, a system that recycles almost everything. Air, water, food, waste, all of it has to stay in the loop. Right now, on the International Space Station, the life support system already recycles a lot. Most of the water is recycled from humidity and even from urine. Oxygen is partially regenerated, but the ISS still depends heavily on resupply launches from Earth for food, spare parts, and various consumables. That works in low Earth orbit, where you're a few hundred miles, a few hundred kilometers up. It doesn't work when you're tens of billions of miles from home and no one's coming back. On a decades-long mission, we'll send the cargo ship later is not an option. Your system has to run almost perfectly on its own. That means growing food, balancing gases, cleaning water, handling waste, and doing it all with minimal losses, year after year. Every small leak, every tiny inefficiency adds up over time. If your system loses even a small percentage of water or nutrients per year, over 30 or 40 years, that can become fatal. Designing and testing something that stable is a huge challenge, and you have to do it before you trust people's lives to it, at high speed, far from any backup. Then you have to decide what kind of ship you are even building. If you want comfort and long-term stability, you think about a rotating habitat that spins to create artificial gravity, with big living areas, farms, workshops, and medical facilities. That immediately drives the mass into the millions of tons if you want something comparable to a small city in space. With near-future propulsion, accelerating a structure that big to any serious fraction of light speed is basically impossible. The energy cost is enormous, the engine size becomes ridiculous, and the fuel requirements blow up. A true generation ship in that sense is almost like moving an asteroid. On the other hand, if you want to actually hit high acceleration and high speeds, you go the other way. You design a sprint ship, something as small and light as you can make it. Maybe tens of tons, maybe a few hundred tons at most. Tight quarters, minimal volume, high thrust, high delta V. That is much more realistic to push to 0.1 C or beyond with advanced propulsion. But now you have a different problem. People are not robots that you can stack in a narrow tube for 40 years and expect them to stay sane and healthy. Cramped conditions, limited privacy, constant noise and vibration, and no chance to go outside except in a suit take a real toll on psychology and biology over time. Even if you solve most of the recycling, you still need a safety margin, a buffer of consumables. You want extra food in case of crop failures. You need spare parts for machinery, extra medical supplies, replacement electronics. You may need backup systems for critical functions like air circulation and power. Every pound of those reserves has to be accelerated with you. Add another ton of food, that is more mass for your engines to push. Add more structural reinforcement, more shielding, extra tools, and your total mass creeps up. As mass climbs, the speed and distance you can achieve with a given propulsion system and fuel load go down, or the mission time stretches out. This is not a small effect. It directly squeezes your distance in one lifetime budget. Now layer the human factors on top. A mission that lasts 20, 30, or 40 years is a human life stage, not a short deployment. People will age, some will get sick, some might die on the way. If you send the crew in their 20s, they will be middle-aged or old by the time they arrive. If you start with older experts, they might not live to see the destination. On very long trips, you have to plan for the possibility or even the certainty that children will be born in space. That means education, childcare, social structure, and medical care for pregnancies and births. You also have to think about how it affects people to grow up in a metal world, where outside is instantly fatal. Medical emergencies are another reality. You cannot evacuate anyone. You cannot call an ambulance from Earth. Your ship has to be its own clinic, maybe its own small hospital, with equipment and trained personnel ready to handle injuries, infections, chronic conditions, and mental health crises. Over decades, the odds that something serious will happen approach 100%. All of this pushes your ship design toward being less like a vehicle and more like a small, self-contained civilization. And every time you move in that direction, you add systems, redundancy, and ultimately mass. So there is a brutal fork in the road. If your goal is to send humans fast and far in one lifetime, you are pushed toward a fast and brutal design. Few people, small ship, minimal volume, minimal life support and shielding to keep them alive for the flight. That gives you the best chance of reaching high speeds and covering more distance before age wins. But it also means high risk, high psychological stress, little comfort, and very little room for error. If you decide that's too harsh and you want a more stable, comfortable environment with a large crew, real gravity, and long-term social structure, you end up building something closer to a city ship. That solves some human problems, but it turns your journey into a multi-generational project. The ship is too massive to accelerate to relativistic speeds with any propulsion we can realistically see in the next century. Your travel time to even the nearest star stretches into hundreds or thousands of years. That means the people who arrive will be the descendants of the original crew, not the crew itself. You've answered a different question. Can humans as a species reach other stars? Not can a single person do it in one lifetime. So the implication for distance is clear. If you insist on everything happening inside one personal lifespan, your design space shrinks fast. Your ship has to be light enough to accelerate hard, but robust enough to keep a small crew alive for decades in a hostile environment, with almost no resupply. That combination sets an upper limit on both your speed and your mission duration. Together, those numbers set a hard cap on how far you personally can actually go. That brings us to the next step in the story, where we stop talking in general and pick specific scenarios. If you accept a more conservative high-speed technology, say a fusion or advanced nuclear ship, that can push you up to about 1/10 of light speed, what does that really buy you? How far can one human go one way at 1/10 of light speed before their time runs out? There's a version of this future where the numbers are still brutal but just barely start to work in your favor. Call it the conservative Starship scenario. You don't get magic engines, you don't get warp drive, you get one serious upgrade over rockets and ion thrusters. A fusion-driven or advanced nuclear ship that can push you up to about 1/10 of light speed. That's around 0.1 C, roughly 18,600 miles per second, about 30,000 kilometers per second. Still far below the speed of light, but way beyond anything we can build right now. To keep this inside a real human life, lock in one more rule. The whole mission, from launch prep to arrival, has to fit inside about 60 to 70 years. That means you launch while you're young, you live most of your life on board, and if you're lucky, you arrive before your body gives up. With those assumptions, you can define your travel envelope. At 0.1 C, crossing 1 light year takes about 10 years of cruise time, not counting acceleration and braking. So 10 years out and 10 years back is already 200 years just for the cruise phases, which is way outside any personal lifespan. Round trips to stars that far away are off the table, but a one-way journey of around 5 to 8 light years starts to look barely possible in 50 to 80 years total, once you account for the time to speed up, the time to slow down, and maybe a little time at the destination. It's still tight, but it's no longer ridiculous. So which targets fall inside that tiny bubble your life can reach? The obvious candidate is the Alpha Centauri system. The main pair, Alpha Centauri A and B, sit at about 4.35 light-years away. Proxima Centauri, the small red dwarf that is actually the closest star, is about 4.24 to 4.25 light-years out. At 0.1 C, a straight-line cruise to that distance, ignoring acceleration details, would be on the order of 40 to 45 years. Once you add a couple of years of 1G acceleration and a couple of years of 1G deceleration, you still land in the rough range of 40 to 50 years one way. That is the right order of magnitude for someone who launches in their 20s and arrives in their 60s. Inside a radius of about 10 light years, there are only a handful of star systems, but some of them have known planets. You are not dealing with hundreds of options, more like a small menu of nearby systems. But for the first time, the phrase, "you could personally get there," is not a fantasy. With 0.1c tech, those few stars within roughly 5 to 10 light years are no longer just dots in the sky. They are destinations that barely fit inside one human life. Now walk through what that life actually looks like if you sign up for this trip. You are in your early 20s when training starts, years before launch. You learn everything: engineering, emergency medicine, life support, navigation, psychology, because once you leave, the crew is all you have. In your late 20s or early 30s, you strap into a ship that is mostly engine, fuel, and shielding, with a small human habitat buried deep inside. The ship leaves Earth orbit slowly at first. For the first year or two, the engines run almost constantly, pushing you toward that 0.1c cruise speed. Under 1G acceleration, your down is the direction of thrust, and your floors are aligned with that pull. Daily life feels like normal gravity, but you know every second of that feeling is being paid for with propellant and power. After the acceleration phase, the engines throttle back. You are now in cruise. You are not burning constantly, you are coasting at about 10% of light speed through deep space. This cruise lasts for decades. You work, you maintain systems, you exercise to keep your body strong, you grow food, you fix machinery, you celebrate birthdays, maybe you raise a small crew family, maybe you do not. Outside the hull, the stars very slowly shift. There are no supply ships, no quick rescues, no visits home. The ship is your entire world. As you approach the target system, the engines come back on, flipped around. For another stretch of time, you and the crew live under 1G again, this time decelerating. Your velocity relative to your destination drops. Navigation teams adjust the course in tiny increments because at 0.1c, small errors add up to huge misses. Years later, your speed is finally low enough that you can begin serious operations in the new star's gravity well. You slide into a wide orbit or aim for a planet or moon that your probes have scouted ahead of you. You arrive in your 70s or 80s. Your hair is gray, your body carries decades of strain from life in a metal shell, but you are alive. And when you look out, the sun is a bright star far behind you, and another star, Alpha Centauri, A or B or Proxima, is now the thing that dominates your sky. You have made it. You get to see another star up close with your own eyes. You step onto a new world or float above it in orbit, and you know you are one of the very first humans to do that. But in this scenario, you do not go back. There is no return leg. The fuel cost and time cost of an out and back mission at 0.1c blows right through any realistic human lifespan. The ship you arrived on might be refitted to move around that new system, but not to sprint back to Earth. If you are lucky, slower cargo or colony ships may follow you over the next century. More likely, you and your crew become the seed population for a small outpost, a new branch of humanity that lives and dies around another star. Earth is a distant place in space and in time. Messages you send home take more than 4 years to arrive. Replies, if they come at all, take more than 4 years to reach you. So for this conservative high-speed future, the answer is tight and clear. With only 0.1c, even with very advanced fusion or nuclear technology, the farthest a single human can personally travel is on the order of 5 to 10 light years, and that's for a one-way trip. Your reachable zone is a small bubble around the sun, but for the first time, that bubble is big enough to include other suns, not just planets and moons. You cannot tour the galaxy, you cannot hop from star to star casually, but you can, in principle, trade your entire life for one jump across the void to a nearby system. That leaves one more extreme question hanging over all of this. If point 0.1c gives you a few nearby stars, what happens if you go all in on technology and push your ship right up against the edge of what physics allows, short of breaking it? There's one more version of this story where you throw almost everything at the problem and push your ship right up against the edge of what physics allows, short of breaking it. In this scenario, you don't fly at point 0.1c, you fly at around point 0.9c, 9/10ths of light speed. To get there, you need engines that are exotic by today's standards, but still based on real physics. Maybe it's a fusion drive running at insane performance. Maybe it's an antimatter engine that finally solved the production and storage problems. Maybe it's a beamed power system, where huge lasers or microwaves from a solar power array near the sun push your ship and keep feeding it energy. The exact hardware can vary, but the key assumption is your ship can reach and sustain roughly 0.9c for long periods. At that point, relativity is not a small correction. It dominates your experience. Time dilation significantly stretches what your personal lifetime can cover in terms of distance. Once you fix the cruise speed, you can talk about your effective travel radius. At 0.9c, if you cruise in one direction for 40 years of ship time, you cover about 36 light-years in distance as measured in the galaxy's frame. If you stay out for 60 ship years, that becomes roughly 54 light-years. From your point of view, those are just decades, the kind of span as a long career on Earth. But because of relativity, Earth sees much more time pass. At 0.9c, the time dilation factor is a bit over 2. For 40 ship years, Earth might see on the order of 90 years go by. And for 60 ship years, something like 140 years. The exact numbers depend on your exact profile of acceleration and braking, but the pattern is stable. Your life stays in the 40 to 60 year range on board, while Earth races ahead by almost a century or more. So what fits inside a radius of, say, 50 light-years from the Sun? A lot more than in the 10 light-year bubble from the 0.1c scenario. Within 50 light-years, there are on the order of a few hundred stars. Some are red dwarfs, some are sun-like stars, some are in binary or triple systems. We already know of multiple exoplanets in that range, and future surveys will find many more. This is no longer just the immediate neighborhood. This is a real chunk of the local stellar population. In principle, with 0.9c capability, your reachable zone inside one lifetime is no longer just Alpha Centauri and a couple of other targets. It's dozens of systems with many potential planets, moons, and belts to explore. Now think about how you actually fly such a mission. One standard architecture is a 1G profile. You leave the solar system and accelerate at around 1G for roughly a year. During that time, your speed climbs steadily and your onboard gravity is just the push of the engine giving you a floor to stand on. Once you're close to 0.9c, you turn the ship around so the engines point forward, and you can either coast for a while at cruise speed, or for certain routes, you might do half the distance under thrust and half under braking. Near the destination, you run 1G deceleration for another big chunk of time, so that when you arrive in the target system, you are back down to manageable velocities, not blasting through at nearly light speed. On board, life is long-term, but still recognizably human. You have years of acceleration, years of cruise, and years of deceleration. Kids might be born and grow up. Adults age into seniors, people retire from ship duties, new crew take over. You have holidays, conflicts, friendships, routine maintenance, education, and all the ordinary drama of people living in a confined environment. The difference is that your entire city is moving at 0.9c relative to the galaxy outside. The outside stars shift slowly in your sky, but inside, human time moves at its usual pace. Your culture on board evolves along its own line, while Earth races ahead faster, because their time is not slowed by relativity. With all that, what is your realistic upper bound in this aggressive scenario? If you want to arrive at a destination and still have meaningful time to do anything there, your personal horizon is capped at a few dozen light years. If you spend, say, 10 to 15 years accelerating and decelerating in total, and 30 to 40 years cruising, you can cover something like 30 to 50 light years in one direction in 40 to 60 ship years. That leaves you with at least some years left after arrival before age finishes the clock. You could visit one system 30 light years away and spend a decade exploring it. Or you could hit a closer system, then hop a few light years to a second one. What you cannot do within one human life is chain together a long list of stars over hundreds of light years. Every extra jump eats into your age and your fuel and your safety margins. Now take that personal horizon and compare it to the galaxy you are in. The Milky Way is about 100,000 light years across. Your 30 to 50 light year reach is a tiny fraction of that, less than 1/10 of 1% of the diameter. Even if you live on the most advanced relativistic starship humanity ever builds, your entire life only lets you explore a tiny patch, a small sphere carved out of one arm of the galaxy. You are sampling a handful of stars in a system that holds hundreds of billions. It is better than being stuck in the solar system forever, but it is still nothing compared to the full map. There is another catch hiding here too. All of this assumed that your engines, shielding, navigation, and life support work perfectly for decades at 0.9 C. The faster you go, the harder those systems have to work, and the more extreme the environment becomes. At some point, practical considerations may force you to settle for speeds lower than 0.9 C, maybe 0.5 C, maybe 0.3 C. If that happens, your effective radius shrinks again. Relativity still helps, but not as much. Your tens of light years may become a couple of dozen or less. So in this aggressive relativistic starship scenario, the honest answer is this. Your personal horizon is a few dozen light years. That's enough to turn other stars from unreachable fantasies into places you could actually go and see. It's enough to make your lifespan overlap with multiple star systems, not just one. But on the scale of the Milky Way, you are still tracing a narrow track through a structure that's 100,000 light years wide. You are, at best, exploring a pinhole through a skyscraper. And if that's the limit at 0.9 C, it brings up one last brutal question. If even the wildest realistic starship only lets you scratch a few dozen light years, what does that say about your chances of ever visiting something like the Andromeda Galaxy, sitting millions of light years away, shining in your night sky but forever out of reach? There's a hard ceiling on this whole discussion, and it shows up the moment you stop thinking about nearby stars and start thinking about other galaxies. The Andromeda Galaxy is the obvious test. It's the nearest large galaxy to the Milky Way, and it sits at a distance of around 2.5 million light years. That number is not marketing, it's literal. A photon leaving the Milky Way on a straight path toward Andromeda needs 2.5 million years to get there, even at 186,000 miles per second, 300,000 kilometers per second. That's longer than the entire history of modern humans as a species. So even if you had the impossible, a ship that could move at exactly light speed, you still wouldn't arrive within anything even close to a human lifetime. You'd be 2.5 million years late. Maybe you think, fine, but relativity warps time, so can't you hack this with extreme time dilation? This is where the idea sounds tempting and then falls apart. Take a ship that cruises at 0.99 C, 99% of light speed. From the galaxy's frame, crossing 2.5 million light years still takes about 2.5 million years, because your speed is still just under C. Time dilation helps you on board, yes. Your clock runs about 7 times slower than Earth. But 2.5 million years divided by 7 is still hundreds of thousands of years of ship time. You are not shaving this down to 50 years. You're talking about lifetimes stacked on lifetimes, even for the crew. You could push closer to the limit, 0.99 C, 0.9999 C, keep approaching light speed so your gamma factor, your time dilation, explodes. In pure math, you can make the ship's subjective time as small as you like by getting close enough to C. The problem is that every extra 9 you add to that speed comes with a huge jump in energy and in physical stress. At those speeds, the intergalactic medium, the thin gas and dust between galaxies, becomes a constant high-energy particle beam smashing into your hull. tidal forces from massive structures, navigation across millions of light years, and the sheer length of the trip all combine into something that's basically a thought experiment, not a mission plan. Energy is the next nail in the coffin. To accelerate even a modest starship to near light speed, you're dumping in kinetic energy in the order of gamma minus 1 times the ship's mass times c squared. You don't need the exact math to see the scale. Take a ship with the mass of a big ocean liner and try to push it to 0.9 c or 0.99 c. The energy required is comparable or greater than the total power output of human civilization sustained over years. And that's just to speed up. You have to slow down at the other end if you want to stop, which demands a similar energy budget again, unless you're happy to blast right through Andromeda and keep going into intergalactic space. A single Andromeda mission at near-sea speeds would consume energy on the scale of entire planetary economies, maybe more. You would need infrastructure not just in space, but in your whole civilization, dedicated to building and powering that one ship. And even if you somehow solve the engineering nightmare of dedicating all that to a single mission, you still have the time problem. The travel time remains on the order of millions of years in the external frame. Time dilation can shrink ship time, but only if you push speeds to insane levels where survival and engineering become almost impossible. There's also the larger structure of the universe working against you. Inside the local group, where the Milky Way and Andromeda both live, gravity holds galaxies together strongly enough that the expansion of the universe does not tear them apart. But beyond that small gravitationally bound region, cosmic expansion starts to dominate. Space itself is stretching, and the farther away a galaxy is, the faster it appears to recede from us. At enough distance, that recession speed exceeds the speed of light, not because the galaxy is moving through space faster than light, but because space between you and it is expanding that quickly. Those galaxies are not just very far away, they're behind a horizon. No matter how powerful your engines get, you cannot catch up, because the distance is increasing faster than any ship or any beam of light can close it. They're permanently out of reach, not just for you, but for any traveler using any technology that still obeys relativity. And as time goes on, more and more galaxies cross that horizon and disappear from any possible travel plan. So now combine all of this. Andromeda is 2.5 million light years away. Even light needs 2.5 million years to get there. A near-sea starship needs a civilization's worth of energy to accelerate, faces lethal hazards at those speeds, and still sees millions of years go by in the rest frame. Cosmic expansion locks most of the universe behind horizons you can never cross. Relativity helps you a little locally, but it does not make an entire galaxy hop into your hand. The brutal conclusion is this. In one human lifetime, the farthest you can realistically go, even with extremely advanced but still physical engines, is a tiny bubble of tens of light years around the sun. In a conservative case, maybe 5 to 10 light years one way. In an aggressive relativistic case, maybe 30 to 50 light years of personal reach. Entire galaxies, including Andromeda, are not just far in a casual sense, they're essentially unreachable destinations for an individual human being. You can see them in telescopes, you can map them, you can study their stars and black holes, but you will never visit them yourself, no matter how early you launch or how good your ship is. That leaves one final step in this whole journey. You have seen Earth escape, inner planets, outer giants, the heliopause, nearby stars, relativistic ships, and unreachable galaxies. So when you put all of that together and ask honestly, how far can I actually go in one lifetime? What hard number do you end up with? And what does that say about your place in the universe? So after all of this, what does your lifetime really buy you in distance if you stack every limit on top of every other? Start from the bottom. With the tech you actually have right now, chemical rockets, your ceiling is the inner solar system. Big launchers like Falcon 9, SLS, or Starship-class vehicles can throw crews and cargo to low Earth orbit, then onto the Moon and Mars. Over a full career, you could ride missions that take you to Mars, maybe a Venus flyby, maybe an asteroid, maybe a long stay on or around the moon. You can cover billions of miles, loop around the sun many times, and spend years off Earth, but you stay inside a band of roughly zero point 0.4 to 1.5 astronomical units from the sun, deep in its immediate neighborhood. Chemical rockets let you tour the inner system in one lifetime, nothing beyond that. Add the next layer, nuclear thermal and nuclear electric engines, plus high-performance ion or Hall thrusters. They push you farther. Trip times to Mars and the asteroids get shorter. Missions to Jupiter and Saturn become more practical in human time, maybe years instead of half decades, maybe months instead of years for certain legs. Robotic missions can be faster and more flexible, and crewed ships can go deeper into the outer solar system. With enough power, you could even send human or robotic explorers to the heliopause, the rough edge of the sun's bubble, at around 100 plus astronomical units. In this regime, a determined person could plausibly say, "I spent my life exploring the solar system," and it would be literally true. Then there's the speculative but still physical layer. Advanced fusion drives and beamed light sails. These are not available now, but they live in the zone where serious engineers can sketch designs. A fusion-powered ship or a massive beamed propulsion system could push a small crew vehicle to around 0.1 c, 10% of light speed. Ultra-light sails driven by huge laser arrays could fling gram-scale probes to maybe 0.2 c. At that point, the conversation shifts from which planets to which stars. You're no longer limited to the sun's gravity well. You're planning crossings between stars in times measured in decades, not tens of thousands of years. When you put all this together, you get a realistic upper bound. With optimistic but not magical tech, something like a 0.1 c fusion or advanced nuclear ship, your one-way frontier is on the order of 5 to 10 light years away. That covers Alpha Centauri and a small handful of nearby systems. With wildly advanced relativistic engines that can sustain something like 0.9 c and keep you alive under heavy time dilation, your subjective lifetime, the time on your own clock, could span maybe 30 to 50 light years of distance. That's the best case: extreme propulsion, extreme shielding, and the ship that is basically a moving civilization, all working perfectly for decades. What does that actually mean in plain terms for you? In the conservative high-speed case, you could personally launch from near Earth and end your life under a different sun a few light years away, maybe orbiting a planet around Proxima Centauri or one of the Alpha Centauri stars. You would trade your whole life for that one crossing, but you would do it. In the aggressive 0.9 c case, you could go farther. You could leave the solar system, hit a star 10 light years away in a couple of decades of ship time, maybe transfer onto another system a few light years beyond that, and eventually die on a world orbiting a star dozens of light years from where you started. The stretch of space your life covers is no longer just a thin ring around our sun, it's a narrow corridor through the local neighborhood of stars. The price, though, is absolute. In both cases, you do not come back. At 0.1 c, a round trip is far beyond 100 years. It does not fit a human lifespan at all. At 0.9 c, a round trip is technically possible in ship time, but by the time you return, centuries will have passed on Earth. The culture and languages you left behind will be long gone. The Earth you remember will exist only in records. For you personally, the moment you commit to a true interstellar crossing, you are saying goodbye to your home planet and everyone on it. Your story becomes a one-way line, not a loop. So the emotional punch is this: your life is too short for the galaxy, too short for Andromeda, too short for most of the universe. You will never personally cross a galactic arm, never span millions of light years, never see another galaxy up close. But if we solve propulsion, shielding, and life support at a level far beyond what we have now, your lifetime is just long enough to reach a few other stars. Not all of them, not many of them, just a tiny selection of nearby systems in a bubble maybe a few tens of light years wide. Inside that bubble, the laws of physics do allow one human body and one human brain to make the trip. And that is the final answer hiding underneath all the big numbers. In one human lifetime, you cannot conquer the cosmos. But with the right chip, you could cross the night between stars, trading the world that made you for a horizon no human has ever seen. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.